Well, while we're waiting to start, I just want to remind people to that you're at the St. John Centre, Royal Astronomical Society of Canada. I'm Gary Diamond, your president. I'd like to just remind people who are just new to Zoom, if you bring your arrow down to the bottom, your things will show up. You can go into chat. You can chat to everybody, or you can chat just to one person in your videos. When we start the meeting, I ask that you turn off your mics because of feedback, so that when one person is talking, they'll be able to hear everybody instead of everybody hearing feedback, or if you're having a cup of coffee or a swig or a drop of rum or taking your medicine. Oh man, I'm getting that.
Hi, Colin.
Hey. Good to see you.
Yeah, good to see you.
So you want questions read out as we go, or wait till the end?
I think we should wait to the end.
Yeah,
Would that suit you best, Collin?
Sure. Doesn't matter.
Okay. I find when questions are asked at the time, some people get lost in their talk.
Yeah, I agree. I think it's good to kind of separate the question period and the actual talk.
Okay. Type of thing. I think we can start our meeting. What do you think, Randy?
Yeah, sure.
We got a count. Yeah. Okay. Welcome to the January meeting of the Royal Astronomical Society over Zoom. It seems like this is the one we're going to be going for the next couple of months. I kind of miss the interaction myself. I find also that we've had really bad weather, and I really had to find people to send in their pictures instead of me going hunting. I'm kind of a little bit busy these days, and so if you've taken any pictures or any drawings, please email me rather than me going searching through tons of emails that you guys have sent out. I'd appreciate that. Tonight we got a great speaker, and the person who's going to introduce our speaker tonight is Mike. Are you there, Mike?
Yes.
You want to take over and introduce our speaker?
Okay.
Thank you very much.
It's my great pleasure to welcome our speaker tonight, Dr. Collin Knight. Collin grew up in Blaketown. He graduated from Memorial in 2014 with an honors BSc in physics and a minor in mathematics. He did his undergraduate honors thesis project in experimental condensed matter physics with me. He co-authored 2 nice publications there, and I'm sure he's kept that up. He then moved to Western in London, where he studied interstellar polycyclic aromatic hydrocarbons with Professor Else Peters. He got his MSc in astronomy in 2016 and continued working on his PhD with Professor Peters. And during his research, he flew as a guest observer on SOFIA, which is the Stratospheric Observatory for Infrared Astronomy in the US on 4 separate occasions. And near the end of 2020, so it's pretty fresh, Collin returned to St. John's. He successfully defended his PhD thesis remotely from here. So tonight he's going to speak to us about mid-infrared observations of nearby galactic nebulae, the relationship between interstellar polycyclic aromatic hydrocarbons and the physical environment, and he's going to pay special attention to the observational aspects of his work.
Okay, I'm just going to share my screen. So can everybody see the screen?
Yeah.
Okay. Thank you, Mike. So hello, everyone. I'm Collin, as you all know. So today I want to talk about my research over the past 6 years at Western University. And so I'll begin with an overview. So essentially, I have a very kind of basic overview, and I will kind of ramp up the difficulty going from basic spectroscopy to more kind of complex intersections between astronomy and chemistry. And then I want to talk about how we can observe these polycyclic aromatic hydrocarbons, or PAHs. So different kind of observational methods we can use. And from sections 3 to 5, I'll highlight some of the major results of my thesis. And then we'll get to questions. So part 1. So in the very basic, we have spectroscopy. You have some light source. If you have some kind of disperser like a prism or a grating, you can break it down different spectral elements spatially. And so you can look at some light source in terms of wavelength or frequency, and look how each of these wavelengths, how the intensity of that light source varies with wavelength. Similarly, all objects have some kind of emit light or heat, particularly stars. You can pretty much characterize them as a black body. So how that works is that for a hotter star will emit primarily at a shorter wavelength and will emit at more radiation per unit surface area. Additionally, notably, humans emit primarily in the infrared at about 310 kelvins. So the electromagnetic spectrum consists of more than just what we can see with our visible light or with our eyes. It makes up a very small fraction, as I'm sure you're all aware. And so that extends all the way from gamma rays at the very high energy or short wavelength, all the way up to radio waves at long wavelengths and low energy. So my studies primarily consist of the mid-infrared and some far infrared. So I'm talking in terms of wavelengths in terms of 1 micrometer to up to about 200 micrometers. So if you look at the sky at different wavelengths, particularly visible versus infrared, a particular object is going to look radically different depending on how you look at it. So for instance, the Orion Nebula, if you look at it invisible, you can just barely pick out the Orion Nebula. Compared to far infrared, say at about 160 micrometers, the Orion Nebula and the sword sticks out very strongly, as well as the other part of the Orion molecular cloud. Similarly, the M81, a galactic source, looks drastically different compared to optical and infrared. And so we're going to come back to this image shortly, just to kind of highlight the importance of these polycyclic aromatic hydrocarbons. And so once again, as you're all probably familiar with ground-based observations, you know that it's very highly dependent on wavelength, or highly dependent on atmospheric opacity. So in visible, you have some distortions, whereas from the UV to gamma ray, you're completely blocked out by the atmosphere. In the infrared, you kind of have a wish-wash of absorption lines from atmospheric gases. So in terms of gamma rays or short wavelengths and infrared, you're kind of best served by space observatories. Whereas radio is kind of like a clean slate, no matter what the weather. So my research primarily consists of these astronomical mid-infrared bands that were first discovered in 1973 by Galactic et al. Using observations from the Cooper Airborne Observatory. So this observatory was able to fly above the majority of the water vapor in the atmosphere. And they found that these broad emission features at 3.3, 6.2, 7.7, 8.6, and 11.2 micrometers. Within the source HG 44179, you may know that as the red rectangle, which is a protoplanetary nebula. So as a brief aside, but we'll tie it all together shortly, polycyclic aromatic hydrocarbons, or I'll refer to them the rest of the talk as PAHs. These are essentially planar molecules comprised of aromatic units or benzene rings that are linked together in like a planar honeycomb structure with hydrogen atoms located on the peripheries. They're found in multiple sources in Earth, some which you're probably well familiar with, such as cigarette smoke, auto exhaust, soot, or charcoals. And here are some kind of basic examples of PAHs. So you have the kind of benzene, naphthalene, pyrene, and chlorine, ovalene are kind of more the type that we kind of expect to see, larger molecules of the chlorine ovalene family within the interstellar medium. But I'm jumping ahead, sorry. Additionally, I want to draw your attention to fullerene or Buckminster fullerene. It's also comprised of benzene rings or aromatic units. And as we'll see later, that PAHs and fullerenes are intimately related. So, originally in the 80s, there are a lot of proposed characters for these mid-infrared bands. So soot, different kind of amorphous carbon molecules or dust grains. However, it was based on observations by Alemandola on the ND5. They were able to show that these bands, on a comparison between the Rhine bar and auto soot, they have the same peaks at 6.2 and 7.7 micrometers. So they are both attributed to some kind of aromatic units. Another group of researchers looked at some reflection nebula and found that the observed temperature of these bands got up to about 1,000 Kelvin independent of distance to the illuminating star. Now, classical dust grains of about 1 micrometers are not hot enough. They're typically in thermal equilibrium with their surroundings of about 30 kelvins. So you can't account for larger kind of dust grains as being the carriers of these bands. Instead, the proposed mechanism was a single UV photon absorption event of large molecules of about, say, 10 angstroms in size. Or for our intents purposes, it's widely accepted these molecules are PAHs. So they become excited through absorption of UV light, and then they relax through infrared vibrational modes, which manifest in terms of stretching and bending modes between the carbon and hydrogen constituents of these molecules. And so that's the currently accepted model for these emission bands. And so here is probably one of the more famous spectrum used to characterize PAH emission in the Rhine bar. So this was taken with the ISO short wavelength spectrometer back in the early, I believe it was either in the late 90s or the early 2000s. So what you can see is that in red, you see the emission from PAHs, primarily at 3.3, 6.2, 7.7, 8.6, and 11.2, each due to different bending and stretching modes. And these are all perched on top of these large kind of plateaus, which are also thought to be attributed to aromatic kind of larger nanomolecules or dust grains of about 1,000 carbon atoms. And underlying all this is a rising continuum due to dust or just typical silicates, and a graphite, not silicate, graphite, but silicates and larger dust grains of about 1 micrometer size. So again, we look at M81, and this image in the infrared is taken with the RAC-8 filter on board Spitzer, which primarily covers the 6 to 9 micrometer region, which is primarily due to PAH emission. So what we see is that this galaxy is alight with emission due to these PAHs. Pretty much everywhere you kind of have visible light, you see PAH emission as well. So the significance of these bands, they account for 20% of the infrared emission within our galaxy and external galaxies. They're seen in a wide variety of interstellar medium sources, such as reflection nebulae, planetary nebulae, young stellar objects, circumstellar medium around AGB stars, or asymptotic giant branch stars, and then the diffuse interstellar medium within our galaxy and other galaxies. It makes up 10% of the cosmic carbon inventory. It plays an important role in the physics and chemistry of the ISM and processes such as the heating of the neutral gas, the ionization balance, and their large surface area provides an ideal site for surface chemistry such as the formation of molecular hydrogen. It's thought that polycyclic aromatic hydrocarbons in the ice mantles of dust grains may also aid in the formation of prebiotic molecules such as amino acids or amphiphilic molecules found in cell membranes. So PA emission is not necessarily constant between the sources. These bands vary with respect to sources and within extended sources. So there's kind of two major groups that can be broken down in terms of PA, or the ionization state. So the 627786 bands all tend to be well correlated, and they're all typically ascribed to ionic PAs, whereas the 3.3 and 11.2 bands are attributed to neutral PAs. So there's just two major groups that are characterized by ionization state. So I mentioned that there's this variation spatially. So this author Bernier et al. 2007 looked at this reflection nebula NGC 7823, or the Iris Nebula as you may know it. They found the stratification of mid-infrared emission components with the respective distance from the illuminating source. So here you have the molecular cloud, and at the interface between the molecular cloud and the neutral region, you kind of have emission from very small grains, or they're also made of aromatic units, what are they, 1,000 carbons. And as you get closer to the star, you get more emission from neutral PAs, so about 50 carbon atoms, and closer, even more so, you have ionic PAs. And these authors did a follow-up study in 2012, and what they found is that even the abundance of PAs with decreasing distance of stars decreases while the abundance of C60 increases, which is a clear indication that the destruction of large PA molecules of greater than 60 carbon atoms may aid in the formation of these fullerene molecules in space. So similarly, in the reflection nebula NGC 2023, Peters et al. In 2017 found that different major PA bands peak at different distances from the stars. And this is attributed to the photochemical evolution of aromatic molecules driven by an increasing exposure to the stellar UV radiation field. So a stronger radiation field is basically causing these molecules to change in properties such as charge, size, and structure. So you go from within a molecular cloud, you have large PA clusters and very small grains. And these become irradiated. So you get a wide range of structure from irregular edge structures towards the PDR front, which we'll define shortly, where you get more regular kind of neutral PAs, and finally you get ionized PAs. And closest to the star, you have kind of a transition into fullerenes. So there's this rich carbonaceous chemistry that I want to highlight that you can kind of trace with these mid-infrared observations. So photo dissociation regions, or PDRs, is where we find the bulk of PA emission. These regions are where you have a far ultraviolet photon flux with energies from greater than 6 electron volts or less than 13.6 electron volts, and it controls the physics and chemistry of the gas. So these numbers are significant, as 6 electron volts is necessary for the photoassociation of molecules, and 13.6 electron volts is, of course, the ionization energy of hydrogen. So these PDRs include all the atomic gas and at least 90% of the molecular gas within the galaxy. So here I show a simple one-dimensional edge-on view of a PDR in green here. So you have a star surrounded by an H2 region where you have primarily ionized hydrogen, and this rains incident UV flux on this PDR interface between the H2 region and the molecular cloud. And we can zoom into this, and we can look at the different layers of this PDR, which starts at the ionization front, where you have a transition from ionized hydrogen to neutral hydrogen. Deeper inwards, you can see different transitions between different atomic species. And notably, the PDR front, where you have a transition from neutral to molecular, neutral atomic to molecular hydrogen. And deeper inwards, you see different transitions between carbon and oxygen states. So these regions are very interesting indeed. So in the next section, I want to talk about how we can observe these piles. Well, we know that you want to look in the mid-infrared, but can we use ground-based telescopes? Well, even at Mauna Kea, which is basically one of the best places for ground-based astronomy at 4.2 kilometers, you have a lot of kind of atmospheric opacity in this mid-infrared wavelength. So all these nice observatories that we have with infrared instruments aren't really ideal because of this atmospheric opacity. So we need to look at other ways of obtaining these observations. In particular, we have space-based telescopes, such as ISO in the 90s, Spitzer, which is the current generation, and JWST, or James Webb Space Telescope, which is going to launch hopefully sometime in the next 10 years, will be the game changer for PA research. However, they're very costly to launch and maintain, as you can probably guess. The demand for observation time on these instruments or telescopes are very high, and they have short operational lifetimes of usually less than 5 years due to the cooling necessary to keep these instruments available for viewing in this wavelength range. So finally, we can kind of get a happy medium in air-based telescopes, such as the Kuiper Airborne Observatory, as I alluded to earlier, and SOFIA, which is the Stratospheric Observatory for Infrared Astronomy. So with SOFIA, you do indeed cut down on a lot of the transmission from atmospheric effects, but you have some left over, so it's not perfect, but these observatories are more versatile, they're much less expensive, and operational times are much longer than typical space-based telescopes. So the general rule is if you can't get time on a space-based telescope, your air-based observatories are the next best bet. So I want to talk a little bit more about SOFIA. It was first commissioned in 2010. It's based out of Palmdale, California. It has an expected 20-year lifetime, and as of 2021, it's still going strong. It's a 2.5 meter reflecting telescope located in the aft section of a modified Boeing 747. And it's able to operate at altitudes of over 12 kilometers, and in some cases, almost 13 kilometers. You have access to 85% of the full infrared range. And they can typically do about 128 hour science flights per year with wildly varying courses. So in some instances, when I was a guest observer, we left from Palmdale, California, we went all the way up to Hawaii and back in one night, or in another instance, we went to California to Michigan, all the way up to northern Manitoba and back in a night, just to track the observational targets of the night. And additionally, you can look at the southern hemisphere objects as well, as they have 1 month per year of a deployment in New Zealand. So here's a schematic of SOFIA. Here you have the pilot station, you have a workstation for educators or guest observatory such as myself. And there's workstations for the SOFIA scientists for instrument control, telescope control, as well as mission control. And here you have this high pressure bulkhead, which on this side you have the scientific instruments, which can basically do whatever you want in the infrared, from photometry to spectroscopy. And then you have this open cavity that can open and expose this telescope to the space object that you want to observe. And the telescope will basically go along a trajectory to track that object for as long as possible. So, conclusion is that air-based observatories and space-based observatories are the best way to go when you want to look at these mid-infrared observations. So now I want to briefly go over some of the highlights of my thesis work. And particularly first, I want to talk about how you can look at path size and characterize it with respect to distance from some illuminating source in a nebula or illuminating source or far infrared radiation field. So we can trace path size using a ratio of 2 of the PA bands, the 11.2 to 3.3 bands. As you may recall, both these are deuterated neutral PA species. They both are comprised of carbon, hydrogen, vibrational modes. Additionally, if you have a PA that absorbs a photon of a given wavelength range, a smaller PA will have a higher internal temperature and thus will emit more at shorter wavelengths. So smaller PAs will emit more at 3.3, whereas larger PAs will emit more at 11.2. So we can compare observed emission ratios of 11.2 over 3.3 and compare with theoretical models of PAs, particularly as done by Rika and all 2012, where we looked at PAs in the Cornean and Ovaline family of different sizes and characterized how this ratio changes theoretically with respect to these different families and different average photon energies. So what you can do is you get your observed ratio, you look at this graph, and you can kind of get an idea for the average path size within a particular pointing. So this is what we set it to do. To do this, we use a combination of air-based and space-based observatories. So we used our SOFIA flight cam photometer to observe the 3.3 band, and we used the Spitzer infrared range spectrograph to observe the 11.2 band. So using that, we were able to characterize this ratio in 2 different infrared sources, particularly 2 reflection nebulae, the northwest PDR of NGC 7823 and the south PDR of NGC 2023, shown here in the visible. So for 2023, we take a crosscut across the south PDR here towards the illuminating source AC 37903. And so what we found here is that ratio is greatest closest to the star, and it decreases all the way to the PDR front where you have a minimum. And so you see a clear decrease in path size with distance from the star. Likewise, in 7023, we take a crosscut across this northwest PDR here, shown in bright orange, towards the star. And we again do see a decrease in path size from close to the star all the way to the PDR front, with this intermediate peak, which I have attributed to this ring-like structure here, which is not found in our 11.2 observations, but it's in our 3.3. And I believe that has something to do with the underlying continuum that we can't necessarily get rid of in our photometry easily. But in general, the trend still holds that we do see a decrease in path size away from the star. And if we take like an overall average of the path sizes for both these sources and compare it with the radiation fields at the PDR fronts, we find the first order that a larger radiation field corresponds with a larger path size, which is kind of what we'd expect. So more UV field corresponds to kind of a more breakdown of smaller paths, leaving only larger species remaining. So conclusions from this study, we see that average path size varies with respect to the radiation field strength and extended objects and between reflection nebulae studied, indicating that we have this photochemical evolution of path species, leaving only the largest, more stable species closest to the star. Okay, so how much time do I have in total?
You can go on. You got another lots of time.
Okay, I should probably take another 5 to 7 minutes.
Okay.
So in the next part, I want to talk about, sorry? Okay. In the next part, I want to talk about looking at PA emission across a PDR. In particular, we look at the prototypical PDR, or the Orion bar. It's called a prototype as it's nearby, well, relatively nearby at 400 parsecs. It's very spatially resolved, and many studies have been done on this PDR. And in particular, it's edge-on morphology. So we can kind of look, if you think back to that 1D schematic, we can look at the different layers within the PDR. And this has been long considered a benchmark when looking at PDR environments. So for this study, we use the Spitzer spectrum. We take two separate pointings, which we refer to as the Orion bar ionized and Orion bar combined. So essentially, this is closer to the star, and this one's farther from the star, but they both cut across this Orion bar here, which is an edge-on PDR. And this theta 1 Orion-C is the primary illuminating source in this nebula, which is surrounded by this H2 region. And so we want to kind of characterize how PA emission varies within both of these apertures. So I want to briefly discuss kind of PDR morphology or orientation, if you want to think of it like that. So as I said, it's an edge-on PDR, which means we can look at the different layers, such as like the ionization front and the different layers in between the ionization front to the PDR front, where we have a transition from neutral or atomic to molecular hydrogen. So we can see we can resolve the stratification. We can see the effects of photoprocessing on the different molecular species that we trace. But additionally, there's also a PDR located behind the trapezium or the illuminating source, as well as behind the Orion bar which is referred to as the Orion veil. So I call these face-on PDRs because what you see when you look at these is essentially all the different layers mixed into one line of sight. So you can't really discern the depth of the PDR, and we're kind of just looking at everything mixed into one big kind of glob. So we want to kind of talk about the effects of these different morphologies on our observed spectrum. So in this case, I take a line cut across this OBC aperture that I showed earlier. And what I find is that all the major PA species peak at the same position within the edge-on PDR. And I should also mention that I also supplemented SOFIA observations at 3.3 so that we can look at all the major PA bands. So while all the PA bands do peak at the same position within the Orion bar, as you move into these face-on PDR, in front of and behind the bar, you see more variation within the PA bands. So additionally, we can use the subcomponents of the 7.7 complex. So the 7.7 has multiple peaks when at 7.6 and 7.8. We take the ratio of those and compare it with the strength of the radiation field. We see that there's a clear kind of anti-correlation between this ratio and the radiation field. So what that means is you can use this ratio as a way to kind of trace the strength of the radiation field. And additionally, we break this into a red and blue group. And what we find is that the edge-on PDR kind of has a narrower slope compared to the face-on PDRs, but they do indeed kind of replicate previous relationships that have been found between these parameters, as shown by Stock and Peters in 2017. Another empirical relationship that we reproduced was between the 6.2 and 11.2. So 6.2 is due to PA ions, 11.2 is due to PA neutrals. And the ionization parameter, which is a combination of physical variables, so the radiation field, the gas temperature, and the electron density, which is related to the gas density. So it's essentially a ratio of ionization and recombination of these PA species. And so again, I break this into two separate groups. And what I show is that the edge-on PDRs in the bar are very well able to reproduce this relationship found between gamma and 6.2 and 11.2, whereas the face-on PDRs show much more scattered and there's no clear relationships. So finally, we see that PA emission profiles are more variable inside the edge-on PDRs. There's clear difference in emission behavior in the edge-on and face-on PDRs. and we're able to reproduce empirical relationships between pod emission ratios and physical conditions. So there's definitely some potential there for using these emission features as PDR diagnostics. So I have one more section to go through, and then I'll conclude. So in this final study, we look at a spatial map of pod emission, which covers both an irradiated nebula and a diffuse outskirts of this nebula. So in this study, we looked at the reflection nebula NGC 133. We took a spectral map of the nebula centered on this illuminating source SVS3 using Spitzer spectrum. And we supplemented this with far-infrared cooling lines taken from the FIFI-LS instrument on board SOFIA. So we have 3 cooling lines from oxygen and ionized carbon. And we also use the Herschel PAX instrument to trace the far-infrared dust continuum at 3 different wavelengths here. So first, I wanted to talk about the pod emission. Generally, there's this general concentric morphology centered around the star, but there's 2 kind of distinct different peak morphologies characterized by the 7.7, which has kind of a very compact peak to the south of the star, and the 11.2 has this very elongated peak that extends well southwards of that. So what it indicates is that ionic and neutral pods kind of have a different spatial morphology within this nebula. You can also look at different pod groupings by essentially, so in this case, we look at the ratio of 8.6 or 11.2 and color code our data to that ratio. So we find 3 different regimes within our spectral map. So the diffuse outskirts of our nebula, and the nebula, we have the strongest radiation field, and there's this transition region shown in cyan here. And so both of these relationships I show here show multiple branches. And so what I found between when I look at 6.2 and 11.2, and I look at the underlying plateau, so the 5 to 10 micron plateau over the 11.2, there's 2 distinct branches characterized by the nebula and the diffuse emission, indicating that there's multiple subpopulations here. So what I mean by subpopulations are groups of pods with different underlying properties, so different charge states, different sizes, etc. Additionally, we can look at subcomponents of the 7.7 and compare with subcomponent of 8.6, and we then see different branches. So essentially what this means is that these emission features kind of have different underlying emission properties, and as well as different kind of structural properties within different astrological environments within our spectral aperture. Okay, so I'll briefly go over how we can derive physical conditions. So from our PAX data, we're able to estimate the far ultraviolet radiation field strength from our far infrared dust continuum. And using PDR models, which I'll just briefly say that you can use their cooling lines that we obtained from SOFIA, along with the far infrared dust emission to derive spatial maps for gas density and gas temperature. And you can combine all these together to get a map for the ionization parameter, which is basically a parameter which traces the ionization to recombination rate of pulse. So next, we look at pod ratios and compare with these physical variables. So what we find is that ratios of the 6.2 to 11.2 or 7.7 or 11.2, etc., they show a tight correlation within the diffuse ISM, but when you get into the nebula, there's a much larger scatter. So meaning it's probably not the best tracer of just the radiation field strength. Whereas we are getting able to reproduce a tight correlation, anti-correlation between the 7.8 over 7.6 subcomponents and both the diffuse and nebula part of our spatial map. And we also uncover this new kind of correlation between G8.6 over G7.6 with respect to the radiation fields in both points as well. Unexpectedly, we did not find any kind of tight correlation between the ionization parameter and 62R11.2, which is surprising, which it could be due to the lack of resolution in our models, or maybe that's what we're seeing here. But there is kind of a weak relationship between the G86 over G76 with gamma, but it's really hard to put any kind of weight into that, as the uncertainties are quite large here. Okay, so from this section, we saw that there's two distinct spatial morphologies traced by ions and neutral pos. So different linear relationships are seen by different branches within our correlation plots, indicating there's different pos subpopulations. And we're able to reproduce some empirical relationships between pod emission ratios and physical parameters, indicating that pos do have a lot of potential as PDR diagnostics, or as ways to trace the physical conditions, but it still needs a lot of work. So last slide, future work. As I mentioned earlier, JWST, the James Webb Space Telescope, will be a game changer for pod research. It has much higher spatial resolution. It covers all the major pod bands from 3.3 all the way up to 20 microns. So one of the early release science missions will look at the Orion bar, which will give us immediate kind of comparison with our current work. And it will allow us to look at much more mid-infrared bright sources on a much higher resolution. So basically, understandings of pos will grow exponentially within the next 10 years, provided that JWST is able to get us the data we need. And so another one of the major goals is looking at pos as PDR diagnostics. And in terms of far infrared emission, SOFIA is basically the only game in town for the next 10 years. So by using SOFIA to kind of get these cooling lines that can be put into PDR models to get the physical conditions, we can compare pod emission with the maps of physical conditions to test the viability of pos as PDR tracers over the full range of observable conditions with matching spatial resolution and matching apertures. Thank you very much.
Thank you very much. Any
Okay.
questions?
Yep, we, Michael, I assume that's Mike Morrow. I can't see the panel of everybody here. Is asking, what are the precursor molecules that react to form polycyclic hydrocarbons?
Okay, so in the interstellar medium particularly, there's kind of two ways to, let's see, there's two main kind of forms of pod formation that's currently accepted. So you have bottom-up processing, where you can have pods form in the outflows of late kind of astronomic giant branch stars, where they kind of form from small carbonaceous species such as carbon monoxide and acetylene. But current models kind of struggle to predict how pods with more than 3 benzene rings can form this way. So that's still an active area of research, in particularly astrochemistry. Another way you can have them form is from top-down processing, or the breakdown of large carbonaceous grains. So essentially they're processed from strong UV fields or solar winds or supernova shocks, which will break these large grains apart, and you'll have freely flying pods of the size that we observe, of about 50 carbon atoms, will be the resulting products.
Yeah, if I could just sort of expand on that question, I guess the thing that surprised me was there's so much more carbon than hydrogen in these things, and they're forming in an environment that I would think is a pretty strongly reducing environment. So I was just puzzled by that a bit.
Yeah. Yeah, I can't really speak to how the Well, I mean, hydrogen is going to be more abundant than everything else. But you can definitely have like other carbonaceous species that can form without hydrogen, such as fullerenes or some kind of alpha kind of carbon chains, which I guess would have hydrogens as well.
Okay, thanks.
Yeah, I'm sorry, I kind of went off track there, but I do see what you mean.
I have a quick question. I understand what nebular cooling lines are, but you've mentioned them many times, so I was wondering if maybe you could just clarify what nebular cooling lines are for the audience.
Right. Yeah, I apologize. I kind of skated over that just to
No, that's fine.
keep the focus on pause. But so essentially, you have these forbidden lines from, excuse me, from different atomic species such as carbon or oxygen.
And when you talk, it doesn't hear you? You don't.
Can you hear me?
Is it, so for clarity, are these the panelists who are talking or are they the guests?
Mother, you're not interfering with the meeting, are we?
Sue, I think your mic is open.
Yeah, actually, I'm trying to ask a question, but I can't get it to unmute. So that's okay. Sorry, I didn't mean to interrupt the proceedings, but I can't get in to ask a question.
So this doesn't necessarily, this is probably not a good figure to show, but these cooling lines, so these atomic species are kind of excited and they cool at far infrared wavelengths, which are optically thin to basically the nebula or PDR, whatever you want. And that allows the net cooling of this gas because it's able to radiate away that gas, or radiate the light from the cloud in question. Does that kind of allude to what you're looking for, or am I?
How the nebula can emit wave energy, basically.
Essentially, yeah.
Yeah. Downshift the UV from the star and get it out of the cloud.
Exactly. Yeah, exactly. That. So we're interested, as I've shown this figure, which is not really great, but they're right now the best way of looking at the physical conditions within these regions. So you can use these models of these lines and compare with observations to get an idea of the actual physical conditions within the nebula.
Yeah. Doug Grushi asks, what kind of technology is used to keep the aircraft-mounted telescope on track? Are the observations continuous during the flight or only during certain intervals?
So the observations, well, the flight path is very complex. Like it's not just a straight line out to Hawaii and back, or where you want. It could, the flight path will turn to keep the telescope kind of looking at the object. And they also have like these line of sight rewinds, which will kind of rotate the telescope back every minute or so just to keep it on track. But like they could look at, say, Orion, and then say it spends 40 minutes on Orion, and then between that they'll turn the telescope or the whole plane to look at, say, a standard star. So the whole flight path is mapped out such that we can look at all the objects that we want to and kind of get all the standards in the background observations between.
You must beam switch a lot to get rid of noise and so on, backgrounds?
Yeah,
back and forth.
Yeah, it's a lot of nods and throws and chops in between. It's like every 10 seconds or so.
Yeah. Wow. Okay. It's not at all like our 5-minute exposures with our cameras on our telescope.
No, it's like I said, it has its advantages and its disadvantages compared to ground-based and space-based.
Sue, I think, had a question, but I don't see it in the chat window. Sue, did you want to ask?
Speak?
Okay, can you hear me now?
Yes.
Yes.
Okay, good. All right. Fascinating research. It's a bit technical for me, I have to admit.
Oh, I just muted. Sorry.
Can you hear me now?
Yes.
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 Okay, sorry. Great research, except it's a bit on the technical side for me. So here's a very non-scientific question for you. What are the implications for life on Earth and, you know, our immediate spatial surroundings for your research on these paths? Because you were saying there are more of them, right?
Yes. They're ubiquitous. They're everywhere.
Right, but have they been increasing over the longer term, as I kind of gathered from what you were saying? And if that's right, what kind of radiation is causing that, and how might it affect us? Because you said yourself, some of these particles are carcinogenic, like benzene, for example.
Yes.
Yeah, okay.
So in terms of direct the context of life, as I alluded to, they've been found in meteorites, and they're also thought to have been able to, as a primary kind of place for primitive life-forming molecules such as amino acids, cell membranes. So in that case, they can directly become like a catalyst to forming life. But in terms of the radiation, I don't think the mid-infrared radiation from PAWS would necessarily have a large effect, but maybe the fact that they're kind of shielding the UV radiation of molecular clouds, they could have, and somehow maybe made it easier for larger molecules to form as a kind of like a shield.
Right.
In the same way that I guess you have molecular hydrogen self-shielding, and as I said, PAWS can also be a great site for surface chemistry to form molecules like molecular hydrogen.
Yeah. It seems a bit of a paradox to me, and I may be completely misunderstanding this, but it's on the one hand, I think what I'm inferring from this is that they might be life forming in the sense that you were saying they could actually influence life development, but they're also carcinogenic at the same time.
Yes.
Potentially. Yeah. So it's kind of an interesting paradox.
Yeah, they're not good for breathing in.
No, indeed. Right. Okay. Thank you very much.
Thank you.
Interesting research.
Thank you very much.
Any more questions, Chris?
I don't see anything in the chat window.
Yeah. I got a question. You said that the pause on your edge-on and your surface were different. Is it because we're looking at them from the edge-on and the surface, or is it? Yeah.
Yeah, I think it probably has a lot to do with the orientation that we're looking at. Whereas, like, we're looking deeper into one layer of the PDR. Whereas when it's face on, you think of it like this, and then you put it like this, and it's all just mashed together, so you can't really see any clear kind of stratification. And so part of my work is trying to entangle what that implies for the pod population.
And I got one little more question. Very simple one. When you were starting off, I know when I do spectrum, I take out the water and the atmosphere when I get my spectrum. And you were saying that you can't take out what you're looking at from the atmosphere. Is that why you have to go with the airplane or the space?
Well, that in terms of space, you don't have to deal with that. You know, you'll have a model for the dust extinction that you can subtract. But in terms of Sophia, they actually do have a model for the atmosphere. So when they're reducing the data, they actually do apply that model and subtract that. So the effects of the atmosphere are accounted for when we get the reduced data. That's a variable.
But you can't take that same filtering for the land telescopes, like on Hawaii.
It's a lot more difficult So
Okay.
early on in my astronomy career, we started with ground-based observations of the pods, and the top 99% was from atmospheric contamination. Only the very 1% top of the mission was pod emission, and we weren't able to use it because it just couldn't get the contrast that we wanted. But it was a beautiful image nonetheless.
Okay. I was just wondering. So it's very difficult to filter it out.
Yeah, it's a good point.
Okay. Thank you very much.
Thank you.
I found it very interesting. If there's no more questions, thanks very much. You are willing to stay on as we do the rest of our club meeting, find out what we do here.
Sure.
Okay. All right.
Thanks for your talk, Colin.
Excellent talk, actually. Excellent.
Thanks very much.
Okay. Let's see. Oh, I got to do calls for reports. Okay. All right.
Thanks for your talk, Colin.
Excellent talk, actually. Excellent.
Thanks very much.
Okay. Let's see. Oh, I got to do calls for reports. So, I was working, and the day before this closest approach of the Jupiter-Saturn conjunction, I went up on top of the hill and got to see it. It was a lot easier to pick it up. This is by phone picture, actually, from my phone. And you got Jupiter and Saturn's just a little bit above there. But that's about it. Jim, are you there? Jim Tracy. Stacy.
Okay. Can you hear me?
Yes, I can.
Okay,
That's a
good.
video.
Anyway, Yolanta wants me to put on the video, but I don't think I want to do that. So,
Oh, that would be
okay.
interesting.
Well, in the past month or so, there was about 4 hours of actually clear sky, and this was only a few weeks after my back operation, so I wasn't able to carry anything out. So Yolanta was very kind to take some gear out, and we took out our quantum 4 Maxitov telescope and mounted it on there, and we forgot the counterweight, so we pointed it at Jupiter and Saturn on that one beautiful night that we had just prior, the one day before the conjunction was of Jupiter and Saturn. So you can see this is my shot here. So this is the only observing I actually did using my own gear. So we have the 4 moons of Jupiter there. And with this particular telescope, it's only a 4-inch telescope, so I was only able to get a hint of banding going on. But we could see the rings, and the viewing was actually quite nice. And there was a lot of nice photographs taken of that. And we were lucky here in Newfoundland to have a few hours just after dusk to actually see this event. So I'm looking forward to the next conjunction in 60 years' time.
Jim, can I ask, was your exposure corrected in your pixel insight to get the detail on both? Or did the image actually do that?
Well, what I did is I took, I think this was 11 exposures, and I took about 100 exposures at about 1/60th of a second, if memory serves. And I just looked through them visually, and I took 11 of the best exposures. And then I actually stacked them in PixInsight using something called FFT registration, which I have absolutely no idea how it works. But I actually used that particular program to stack these photographs, and it seemed to work okay. Anyway, what I wanted to talk about, since we don't have very much in the way of clear skies here in Newfoundland very often, I noticed that I got an email last week about the RESC selling image data from the RESC's robotic telescope. So I thought I'd take advantage of this and this opportunity to basically support the telescope by buying some of the products of that instrument. So this is a picture taken from the RASC site that shows the 16-inch Ritchie-Chrétien reflector Cassegrain telescope. And it's mounted on a Paramount Software Biscay robotic mount right there. So this, I think, is this was provided by the manufacturer, but I think it's a relatively accurate depiction of what the RASC's robotic telescope might look like. And it's equipped with a CCD camera, which I've never used before. The SBIG STX 16803 doesn't mean anything to me, but it's a 4K by 4K CCD camera with 9 micron pixels. And with this particular telescope, it's got a focal length of over 3,500 millimeters. So it's basically half an arc second per pixel. So it's actually fairly high resolution. And it comes with all kinds of narrowband and broadband filters for various applications. Mounted on top is an ordinary astro-modified Canon 6D camera connected to a 200 millimeter f2.8L telephoto lens, and that's for wide field shots. So last week I bought the access to this data set, and this is one of the examples of the wide field shots from the Canon, the Canon camera. And this has got basically a field of view of approximately 12 degrees from corner to corner. And that very, very bright object you see down in the lower right is actually Jupiter. I actually didn't recognize that. I thought it was a planet, but I just went into Stellarium and dialed in the date of this particular photograph, and sure enough, that was Jupiter. So anyway, so this is an example of some of the wide field shots. So this is also called at the very center, there's a globular cluster towards the upper center. Yeah, there, right there. Thanks, Gary. And then, of course, the dark nebula called the Prancing Horse is perhaps visible down on the bottom there. That's good. Anyway, so that's an example of the wide field shots. Then I turned my hand to my very first attempt at LRGB processing. This is the first Messier object, the Crab Nebula. And this was my first attempt at imaging that data. So this is what basically you see much brighter colors in photographs, but I found that the data comes out of the camera is I basically calibrated it with the photo calorimetric data from PCC in PIX Insight. So this is more accurately what you would see normally. The problem with the saturation though is that often the imagers basically push this too far. So anyway, so this was processed to my own personal tastes, which is a little more subdued than some of the other things you might see. The physics of this as well, of course, the Crab Nebula is a supernova remnant, and at the center of that, one of a pulsar is basically energizing this nebula. And there's one more example, which was probably germane to the talk today. This is a stellar nursery. This is sometimes referred to as the embryo nebula. In this case, it's IC 1333, and our speaker was talking about NGC 1333. I don't know if they're similar or the same or completely different objects, but anyway, this is a rather interesting stellar nursery. The the stars that are enveloped in this cloud of dust, which we now know is made up of complex city compounds called PAWs, and they emit at all kinds of different wavelengths. But in this visual photograph, most of the stars inside that cloud cannot be seen, except for the dull glow that you might see. The brighter stars in this nebula are only about 1 million years or less old. They're very young. And the dusty and the reflecting nebula is the blue is characteristic of light reflecting in the dust, just like the light reflects in the sky. So that's that characteristic blue color. So you can see there's a very dirty, complex region of the sky. So yeah, so anyway, I just thought I'd put in a plug for those people who are starved for data for their astrophotography, that now there's 2 years, 2019 and 2020 data that are now available for what I think is an absolutely fantastic price. And it's certainly cheaper than renting the telescope, I think, by the hour. So I just thought I'd put that out there for people to think about and support your local RASC robotic telescope project.
Thanks very much, Jim. Excellent work. Chris, are you there?
Oh, yes.
Yeah.
I'm still here.
All right. You didn't give me much information on this, so you can chit chat about this.
Yeah. Yeah, that one nice clear evening we had. My daughter has a little 5-inch tabletop reflector, and we the only place on the property where we can actually see low enough in the sky to have seen the conjunction was from the end of our driveway. So, and we only had like a 45-minute window, of course, to see this. So we grabbed the telescope, put a mat on the end of the driveway, sat on the mat, and the telescope wasn't tracking, of course, but I did put a camera in the eyepiece. I think it's QHY's new Q53462, the little infrared sensitive one. Anyway, high frame rates, let the Jupiter and Saturn drift through the field, shoved it through PIPP to align everything, then stacked that in Registax. And I shot the video with a very nonlinear gamma, so to depress the dynamic range. And that's what kept the moons and Saturn in the exposure range without blowing Jupiter out of the water entirely. So, yeah, could have tried a little harder, I suppose, but I'm yeah, moderately pleased. I also took cell phone shots at the eyepiece. First time I've ever stooped as low as taking cell phone shots at an eyepiece. And you know what? It works. So, you know, anything you can use to record, especially if you're desperate and you're about to run out of time, do it. Oh, yeah. And yeah, this turned out using the same camera, very sensitive, very high frame rate, but this time installed on a 12-inch ACF Meade Schmidt-Cassegrain, basically out in the little dome out in the backyard. And this was actually to start an observing session, which rapidly went south because everything frosted over and dewed over. But Mars was at the beginning of the session, and the corrector plate stayed clear. And hey, when you shoot at 100 frames a second and you shoot what, 6,000 frames, a couple thousand frames added up. Yeah, so there's even some detail on the gibbous planet. That turned out okay, I thought. And Uranus was immediately after Mars that night. And yeah, we're no longer shooting 100 frames a second here. We're shooting like 5. And so very fuzzy frames. I was happy just to get the color. I didn't play with the color at all. I just left it as is. And I'm still trying to take a better picture of Uranus from the yard. It's darn difficult to do from urban environments because the air is so turbulent.
Very good, Chris. Thanks very much. Now, Randy, are you there? This is your conjunction picture.
Well, one of maybe 500 that I took over those few days.
Well, I only put up one.
I know. We had great discussion about the fifth moon during that period. As everybody noticed, obviously it's very difficult to get both planets due to the differing magnitude differences there. Anyhow, that was just one I took, so nothing spectacular.
What camera did you use?
That's a Canon M3 connected at that time prime focus to a Celestron ED80. And I didn't have enough back focus, so I ended up actually just yesterday a 3.5-inch extension tube for 2-inch. So maybe that'll do me for some of this stuff. Yeah, same night. At this time I had my eyepiece and my Barlows precariously at the very edge of the screw, just trying to get the back focus that I couldn't possibly get. So anyway,
nice detail.
That's almost like tonight's moon, isn't it? A little bit, another day or so, I guess.
Nice shot. Thanks, Randy. Mike, are you there? Michael.
Mute here. So this was December 28th, which I think was probably the same night that Chris did. So this was kind of a last shot at Mars. But this was using the ED80, and Randy was just talking about the issues with that sort of thing. So fortunately, I do have an extender that came with my Dob. So I had an extender and a Barlow to get anything at all. So there's not much there, but it was using a fairly small aperture in the ED80. And so I was happy to get anything at all. There's a little bit of, you can see a little bit of something on the surface there. So that, and that was a night when I think it got cloudy pretty quickly. There wasn't much time to do things. And as Chris said, things were frosting up too. So that's December 28th.
Okay.
That's about 1,200 frames. And well, that's not quite as focused as it looks on mine, but that's okay. So this is the same night, and the clouds were coming in, so I just did Orion because it's kind of the beginning of the winter, and that's only about, they were 8-second exposures, and that's about 15 exposures. But I think the original was a little more focused than that one. But
okay.
And the double cluster. So again, yeah, it was focused differently than that, but that is the double cluster. So those are the two things I could get that night, and it's the same thing. It's about 2 minutes of exposure.
Well, thanks very much. Nice shots. Jim Johnson, you there? Are you there, Jim? Jim, are you there? You were there earlier.
Should move on, Gary.
Nice crab, Jim.
I guess he lost him. He is at sea, so that's M1 that he took what he's set up. Didn't send me any information. So, and there's M15.
Nice.
I want to thank everybody who took part. Okay, and now. Nikolai, are you there to tell us what's up the week? the month?
Yes, I am. Do we have time?
Yes, we do. There you go. We have it now, Nikolai.
Okay, can you hear me?
Yes.
Okay. Sorry, I just switching from between the phone and the laptop is a bit strange. Can you hear me now?
Yes.
Okay. All right. So there's actually not a whole lot going on. So I'll go through this fairly quickly. So this is the sky this month. It's available on our website. You can reference that. It's updated once a month. And it starts with sunrise, sunset, and other sun-related phenomena for today. As you can see, the day is 9 hours and 8 minutes long today. Then it moves on to bodies of the solar system, specifically planets and Pluto, rise and set time. And then it has the current picture of the sun. This was taken today. And it has a group of sunspots here to just off the lower left limb. Pretty decent group here, considering how it's been. Although there has been an uptick, in the last, few weeks. And then we have planets all night. Actually, that's a mistake. I apologize. Mars and Uranus should actually be evening planets. I think this title here should say evening planets. So Mars is visible low in the evening sky, but it's too small for meaningful observation. Uranus is also visible very low in the evening sky into February. And we do have morning planets, Jupiter and Saturn, still close to each other following their spectacular conjunction. So they have switched to the other side, and now they are morning planets rising just before the sun. And they will actually have a really nice conjunction with Mercury early in February. We also have Venus, which will disappear, as it approaches its solar conjunction in early February. And with how slowly it moves in the night sky, or in the sky, it won't be back until mid-April. And then, yes, there's Mercury, which goes from evening planet to morning planet as we go from January to February. I just realized I don't have camera on. Not that it's critical, but that's okay. You're looking at the presentation, not me. Here's the comets. Again, nothing going on. The brightest is, magnitude 10. So, and even, the prospects don't look too spectacular. We have the current asteroids, current supernovae on this link, which I didn't check, but looks like the brightest one is 12th magnitude. Meteor showers, nothing. Again, pretty quiet on that front. And we do have a list of dark sky objects for January and February. The brightest and the highest in the sky that you can see with a telescope and with binoculars. And then a couple of passes for the ISS, which won't be until February 9th. So that's also, everything is really quiet. This is the observing calendar for January. is our monthly meeting, which is today. And then there's February. Again, not much going on. So pretty quiet, which is, I guess, okay, because our weather is terrible. But yeah, that should be it. Does anybody have any questions?
Any chance of a clear sky in the next month or so?
Maybe you should try tomorrow night.
I've
Well,
actually started observing in radio, just barely beginning radio observations successfully. So, I can see the Milky Way through all this snow and cloud. I'll talk more about it later.
okay, thanks very much. Thanks, Nikolai. Greatly appreciate it. Randy, any more business? Does anybody have any business?
If people aren't connected to the RAC National, they do have mailing lists you might want to look at. Go to the national website. There's a members, what are they calling, a members session, town hall session coming up on the 24th. If you have anything you want to say to the national executive and such, that's one way to do it.
They also have, you can join meetings. They're also doing work on Explore the Universe. So check the national office and see what things are on during the month that you may want to attend by Zoom. It's quite fun, actually.
One more note, Jim Johnson just got his deep sky astrophotography certificate. You can see all these certificates, by the way. The material that people present is on the website, so you can actually see the deep sky photos that they submitted in order to get their certificate. Oh, I should mention as well, in case you did get an early renewal notice, there was a bit of a glitch in the national IMIS system, and they mistakenly sent out renewal notices for anyone who was renewing in November. So I think you probably got a note from Phil Goff about ignoring that.
Okay. Does anybody have any other information? Anybody have any questions? Wow. Very quiet meeting. I guess long times of no clear sky has made everybody silent and quiet. I kind of like that. Usually somebody wants to hang me. We're looking for suggestions for more speakers. I want to thank Collin Knight for giving this great talk. Opened my eyes on a few things I didn't think about before. Got to do a bit more research on that. Okay, Bernard, hey, how's your observatory? Have you been doing anything?
No, like you guys, can you hear me okay?
Yes.
Yeah, like you guys, the weather has been really bad. I did get up for one night there during Christmas, and it clouded over before the night was gone, and it was, I think, was just about a full moon that night too, so wasn't too good. And the conjunction there of Jupiter and Saturn, you guys had it better than I did on that few nights there. I was up there waiting, and there was a chance that the clouds might clear, but it didn't. I did get a picture, but it was through the clouds really, so it didn't turn out that good. So no, it hasn't been too much happening. I did get a new camera. I got one of those that Chris mentioned there. I think he's got one like it, the ASI 294 MC Pro, and really hasn't got a chance to really test it out yet. So waiting for clear skies.
Okay. All right. Yes, Nikolai.
I do have a picture of the conjunction as well. I apologize for not forwarding it for the observing session, but I completely forgot about that. So if we have time, I'll show it for very quickly.
Yeah.
So
I don't know if we're running out of time, but yes, please share it.
Might be, but here it is. Can you see that?
Oh, you must have been up the same day I was.
Yeah. So that was that clear night, the day before.
Is that it here?
And zoom in. Here's
They're there.
Jupiter and Saturn.
Yeah.
What were you using?
So this is just with my camera, Canon 6D.
Right.
There's this one as well, a little bit darker. Anyway, I had two friends with me who had, I had my telescope as well, two friends with me who had never looked through a telescope before. And they had always been interested in astronomy. So their first view ever through a telescope, they got to see Saturn and Jupiter together.
Wow.
So they were absolutely stunned by that. And the fact that Jupiter had the 5th imposter moon, that was just, I wasn't expecting it either, but we had to quickly figure out which one was the odd one out. I looked at my Jupiter app on my phone and figured out that the one in the middle was the star, but it looked just like a moon. So we were all in awe. It was such a great night. Definitely inspired them to, one of them wanted to buy a telescope basically the next day.
Good luck.
Yeah. Oh, excellent.
Nice way to start.
Yeah.
As usual, Cabot Tower overlooking the city is a great backdrop.
Yes.
Okay. Shall we call it an evening?
I'm going to go back to looking at the Milky Way through the clouds.
Yeah. That sounds like a
yeah. You're working on 2 radio telescopes, aren't you, Chris?
Yeah, I'm well. I don't know what I did with the simple Yagi antenna. Devilishly intricate things to make, and you have to watch it when you're walking them around because they stab you. So this is just a rectangular waveguide. Now I'm not a radio astronomer at all, right? So this is all brand new to me, and it's a lot of fun. So this is just an empty solvent can, paint thinner can, and a quarter wavelength probe is put into the one side of the can, the right distance up from the bottom. It's all geometry because well, this is for H1. This is for the electron spin flip line of neutral hydrogen at 21 centimeters or 1420 megahertz. And I finished the probe in the can. And I said, you know what? I don't even have the reflector on yet, the horn that goes on the front. I'm just going to stick the waveguide out and just test the receiver, and it's seeing signal without a collector, and it's real signal. So this is cool. This will be really good once there's an actual photon bucket there. Right now the collection area is like this.
I see.
You guys probably can't see it. That's oh God, I don't know. That's the can I point blind? So that's the display, and it's noisy because I've got this laptop which is very noisy, and there's a poor pathetic little thing on the deck inside a plastic bag because it's snowing. But again, I don't have anything to show, so I'll put something together and talk properly about it at some other time. But it is kind of neat to see anything celestial with the clouds.
Anyway.
Maybe this is a very tricky kind of question, but is it possible, do you think, to make 2 or several of these and set them out and try to have them looking at the same area of sky and to try to integrate that somehow?
Absolutely. Baby steps right now, but
yeah,
hey, it would be nice. This is a project. This is not a complicated, project. I simply want to take a picture of the Milky Way looking down on it from above. Weather independent.
Yeah.
That's all. So you looking at different longitudes along the Milky Way, the gas cloud you're seeing, the hydrogen in the spiral arms you're seeing, because the whole galaxy rotates differentially. Some of them are going to be receding from you, depending on the angle, longitude you're looking at. Some of them are going to be approaching you. There's going to be a Doppler shift. You can actually untangle the peaks you see, and basically, given a rotational model, you can turn those peaks into distance away from you. and the other coordinate is the angle around you. And between those two things, you can build up a picture of the galaxy as seen from above. So that's my project. So stay tuned. But if you had an interferometer, you could have a much sharper picture. Now, as to whether or not I'll be permitted to put 3 antennas on a residential property, by
Chris?
my wife, yes?
Maybe next month or the month after. I think we got a gap in our speakers. Perhaps I was thinking maybe we could have another members' night. Have a few things. You might want to just casual. Don't have to prepare anything, but certainly you haven't got. How much snow interferes with you? I mean, real snow, not the radio snow.
It was snowing last night. On the little plastic baggie, didn't have any effect whatsoever on the H1.
Okay.
Now, snowstorm, I'm going to actually bring that in this evening ahead of tomorrow. And I want to put a horn on it and see how much better things are once the storm passes. But it's looking pretty good.
Yeah, we're not going to get.
Very
We're not.
The advantage with microwave frequencies 1 to 4 gigahertz is very well. Collin, in your talk, you showed the atmospheric windows, and this one's wide open. There's almost nothing, and that's true not only through the terrestrial atmosphere, but through the interstellar medium as well. It's a really transparent band. So if that's your game to look at hydrogen, neutral hydrogen, that's a good place to look.
Okay, Gary.
Question, Chris?
Oh, go ahead, Vern.
No, I just I work at electronics all the time, antennas and that sort of thing. Just wondering, what did you have a receiver on that thing to amplify it, or before you got the picture in your computer? Or?
Yeah, this is all possible because of modern electronics. This is one of these software-defined radio things. These little USB dongles you plug into your computer, and an ultra-low noise amplifier and filter that plugs into the front of that. These things are all made for H1 observation now. You can buy these things specially. They're not expensive. Amazon even sells them. For let's see, the receiver is about $40 and the filter is maybe 60. So this is not expensive to get into.
Okay, sounds very interesting.
So
you can follow him and his fellow radio guys on our RASCN talk. They fill it up. It's pretty good, actually. I've been following it. I was trying to find a picture of you, Phil, and me in front of the women's washroom with the radio telescope, getting observations of Jupiter satellites in Terranova National Park. But I wasn't able to find it. Do you remember that?
Okay, yeah.
That's a while ago.
Yeah. Did
That was
we
the only
actually
place that
hear
had a plug.
anything?
Boy, you got some memory, Gary.
Well, it just so happened I was going through albums the other day, and I came across it, but I couldn't find it now. Anyway, I think we'll sign off for tonight.
Okay. Good night, everybody.
Good night, everybody. Take care.
Thank you, everybody.
Good night.
Again, night.
Thanks.
Yes,
Thanks, Colin.
Thanks very
Colin.
much, Colin.
Great job.
Bye.
Good night.